Earth after dinosaurs. The secret history that schools rarely explain. 66 million years ago, a rock 11 kilometers wide slammed into the Yucatan Peninsula with the force of 10 billion atomic bombs. Within hours, wildfires swept entire continents. Within months, the sky turned black with soot and sulfur. Within a few short years, roughly 3/4 of all species on Earth were gone, including every non-avian dinosaur that had ruled the planet for over 160 million years. Slow fade from fire to a quiet, ash-covered forest floor. A small, shrew-like creature emerges from a burrow. But this isn't a story about an ending. It's a story about what happened next. The 66 million years most classrooms skip in about 90 seconds on the way to talking about humans. In that time, a world of rat-sized survivors rebuilt an entire biosphere from scratch. Giant fungi grew taller than trees. Whales walked on legs. 10-foot-tall killer birds hunted horses the size of house cats. And through a chain of accidents, a mountain range, a shifting climate, a strip of grass, one particular branch of tree-dwelling primates ended up asking where all of this came from. This is the Cenozoic era. This is Earth after the dinosaurs. Act 1. The world that survived geological time chart, dinosaur era, fading to Paleocene label. Scientists call the age we're about to explore the Cenozoic, literally new life, and they split it into smaller chapters. The first of these, the Paleocene, began the moment the dust settled, and it was less a triumphant recovery than a slow, grim crawl back from the edge. Barren, ash-gray landscape slowly greening over illustrated time-lapse. For the first several 100,000 years, Earth was a ruin. Photosynthesis had all but stopped. Ocean food chains collapsed from the bottom up. On land, forests that had taken tens of millions of years to mature were reduced to fern-choked wasteland, a phenomenon geologists actually call the Fern spike, because ferns, which recolonize disturbed land fast, are almost all that shows up in the fossil pollen record for years after the impact. The animals that made it through shared a few things in common. They were small. Nothing over about 25 kilograms survived on land. They could burrow or shelter in water or eat almost anything. And critically, they were not dinosaurs. With the dominant reptiles gone, a strange assortment of survivors, early mammals, crocodilians, turtles, and one very important group of dinosaurs that had already evolved feathers and flight, inherited an empty planet. Illustration of early Paleocene mammals, small, generalized, mouse to badger sized. That last detail matters more than most documentaries admit. Birds are dinosaurs, evolutionarily speaking, the one lineage of theropod dinosaur that made it through the extinction. Every hummingbird, ostrich, and pigeon alive today is, technically, a small feathered dinosaur that dodged the apocalypse. But it's the mammals that took over the ecological space dinosaurs left behind. And they did it fast, geologically speaking. Within a few 100,000 years, something remarkable starts showing up in the fossil record. Mammals getting bigger. Much bigger. A creature called Pontolambda appears within the first million years after the impact. Sheep-sized, an evolutionary experiment in scaling up a mammal body plan that had spent 160 million years staying small to avoid being eaten. Comparison graphic, pre-impact mammal size range versus 1 million years post-impact. Within 10 million years, some land mammals reached the size of a small rhinoceros. This is one of the fastest known bursts of evolutionary size increase in the fossil record. And it happened Because for the first time in the history of complex land life, nothing was hunting them. Ast 2. The hothouse and the age of experiments. Global temperature graph, spiking sharply around 56 million years ago. Around 56 million years ago, something happened to the planet's thermostat. A massive release of carbon. The exact source is still debated among geologists, with volcanic activity in the North Atlantic as the leading suspect, pushed global temperatures up by 5 to 8 degrees Celsius in just a few thousand years. Geologists call it the Paleocene-Eocene Thermal Maximum, or the PETM, and it turned Earth into a genuine hothouse. There were no polar ice caps. Crocodile relatives lived above the Arctic Circle. Palm trees grew in what's now Wyoming, and the oceans acidified so severely that entire groups of deep-sea organisms went extinct. A warning, some paleoclimatologists now argue, that reads uncomfortably close to modern carbon emission trends, though on a vastly slower timescale. Lush, humid Eocene forest illustration, dense canopy. For land life, though, the PETM's heat was rocket fuel. This is the Eocene, arguably the strangest chapter in mammal history, a genuine age of biological experimentation, because evolution hadn't yet decided what a large land mammal should look like. Consider Uintatherium, a rhinoceros-sized herbivore with 6 blunt horns on its skull and saber-like tusks, despite being a plant eater completely unrelated to any horned mammal alive today. Or the entelodonts, sometimes nicknamed hell pigs, bus-sized, warthog-faced omnivores with bone-crushing jaws, more closely related to whales than to actual pigs. Illustration of early whale ancestor, Pachycetus, on land near water. And speaking of whales, this is where one of the best documented transitions in the entire fossil record takes place. Around 50 million years ago, a wolf-sized, hoofed land mammal called Pachycetus began wading into South Asian rivers to hunt fish. Its descendants are a case study in evolution, captured almost frame by frame. Ambulocetus, the walking whale, with a crocodile-like body and functional legs. Rhodhocetus, with reduced hind limbs and a more powerful tail. Basilosaurus, 40 feet long, fully aquatic, but still carrying tiny, useless vestigial hind legs, a biological leftover from its walking ancestors that survives in whale skeletons to this day. Within roughly 10 million years, a blink of an eye in geological terms, a land mammal became one of the largest predators the ocean had ever seen. Split screen, Pachycetus to modern blue whale skeleton transition. This is also when primates first appear in force. Small, large-eyed, tree-dwelling animals, the direct ancestors of every monkey, ape, and human that would ever exist, were quietly living in the Eocene's dense, warm forests, completely unremarkable among the giant hell pigs and horned herbivores around them. Nothing about them looked destined for anything. Act 3. The grass that changed the world, cooling climate graph, approximately 34 million years ago, ice sheets forming on Antarctica. Around 34 million years ago, the hothouse ended. Continental drift had pushed Australia and South America away from Antarctica, opening a channel of ocean that let a current circle the frozen continent uninterrupted. That current, the Antarctic Circumpolar Current, effectively insulated Antarctica from warmer waters, and ice began to build for the first time in tens of millions of years. This is the boundary between the Eocene and the next chapter, the Oligocene, and it triggered a mass extinction of its own, quieter than the asteroid, but reshaping the planet all the same. Many of the Eocene's strange, tropical forest experiments died out as forests shrank and climates dried. Forest thinning into open woodland, then into early grassland. Time lapse. And into that drier, cooler world came something deceptively small: grass. Grasses had existed in patches since the dinosaurs, but it's only now, in the Oligocene, and especially the following epoch, the Miocene, that they exploded across entire continents, forming the first true grasslands and savannas Earth had ever seen. This sounds like a minor botanical footnote. It was not. Grass is abrasive. It's packed with microscopic silica particles that wear down teeth, and grasslands offer nowhere to hide from predators. Together, these two facts triggered an evolutionary arms race that reshaped the entire mammal kingdom. Horse evolution sequence: Eohippus to modern Equus. The textbook example is the horse. Early horse ancestors like Eohippus were dog-sized forest browsers with soft, low-crowned teeth and multiple splayed toes suited to soft ground. As grasslands spread, horse lineages that could run fast on open plains with fewer, harder toes and grind down tough,
These horses
gritty
evolved
grass
high-crowned
with tall,
teeth to
ridged
grind down
teeth
tough.
Had an overwhelming survival advantage. Over roughly 20 million years, that pressure sculpted the modern horse, toe by toe, tooth by tooth. It's one of the most complete evolutionary sequences in the fossil record, and it's a direct product of a single plant conquering the continents. Illustration of Miocene savanna, mixed herds, early elephants, saber-toothed predators. The same pressures produced pronghorns capable of sprinting over 80 kilometers an hour, herding behavior in ungulates as a defense against open plain predators, and true saber-toothed carnivores built to ambush fast prey in open terrain. Grass didn't just feed the Miocene world, it built its bodies, one selective pressure at a time. And it was in this changing, drying, grass-covered world that our own ancestors faced a choice. Act 4. Out of the trees, shrunken forest map overlay on East Africa, approximately 10 to 7 million years ago. By the late Miocene, Africa's climate was drying, and its once continuous forest canopy was fragmenting into patches separated by open woodland and grassland. For tree-dwelling apes, this was a crisis and a fork in the evolutionary road. Some lineages stayed with the shrinking forests, adapting to a life increasingly confined to smaller patches of trees. These are the ancestors of modern gorillas and chimpanzees. But at least one lineage began spending more time on the ground, moving between isolated trees across open terrain. Laetoli footprints, Tanzania, actual fossil trackway. The evidence for what happened next is written directly into volcanic ash in Tanzania. At a site called Laetoli, a set of footprints, preserved by a rain-dampened ashfall roughly 3.6 million years ago, and then buried and hardened, shows a small group walking upright, on two legs, with a stride pattern essentially indistinguishable from a modern human's. The footprints belong to Australopithecus afarensis, the same species as the famous fossil skeleton nicknamed Lucy, discovered in Ethiopia in 1974. Why walk upright at all? The honest scientific answer is that no single explanation has won consensus. Leading hypotheses include freeing the hands to carry food and infants, reducing the body's exposed surface area to the punishing equatorial sun, and improving energy efficiency for traveling long distances between shrinking, scattered patches of forest. What's clear from the fossil record is the order of operations. Our ancestors were walking upright for well over 1,000,000 years before their brains began to noticeably enlarge. Bipedalism came first. The big brain came later. Skull comparison sequence, Australopithecus to Homo habilis to Homo erectus to Homo sapiens. From there, the human family tree gets genuinely bushy. And this is a point most school curricula compress into a single misleading line of skulls, marching left to right, each one a little more upright than the last. In reality, at various points over the last 3,000,000 years, multiple human species coexisted on the same continents at the same time. Homo habilis, an early toolmaker, overlapped with several Australopithecine species. Homo erectus, the first of our relatives to leave Africa entirely, reaching as far as Southeast Asia by around 1.8 million years ago, coexisted for a time with Homo habilis in East Africa. Far later, Homo sapiens shared the planet, and in some regions the same forests and river valleys, with Neanderthals in Europe and Western Asia, and with the more recently discovered Denisovans in Asia. And ancient DNA confirms our species interbred with both. World map showing hominin dispersal routes over time. Human evolution was never a straight line. It was a sprawling, overlapping family of species, experimenting with walking, tool use, fire, and cooperation. Most of them dead ends, with only one branch surviving to the present. Act 5. The Ice Ages and the Giants that Vanished. Glacial ice sheet advancing over a landmass. Time lapse. While our ancestors were spreading across continents, the planet itself was locked in a rhythm of ice. Beginning around 2.6 million years ago, Earth entered the Pleistocene, the true Ice Age, though an Ice Age is more accurate, since it was really a repeating cycle of roughly 40 glacial advances and retreats, driven by small, predictable wobbles and tilts in Earth's orbit. At the coldest points, ice sheets over a mile thick buried much of North America and Northern Europe, and sea levels dropped so far that land bridges emerged where oceans usually flow, connecting Siberia to Alaska and linking many of Southeast Asia's islands into a single continuous landmass geologists now call Sundaland. Ice Age megafauna illustration: mammoths, giant ground sloths, saber-toothed cats, dire wolves. It was during these glacial cycles that Earth hosted its last great age of giants. Woolly mammoths and mastodons roamed the northern grasslands. Giant ground sloths, the size of small elephants, browsed in the Americas. Saber-toothed cats, dire wolves, and short-faced bears, the largest land predator ever recorded in North America, hunted across the same plains. Australia had its own suite of giants, a rhino-sized wombat relative called Diprotodon, and lizards over 20 feet long. And then, in a span of time that is, geologically, almost instantaneous, nearly all of them vanished. Most large-bodied Ice Age mammals went extinct within a window of roughly 10,000 years, concentrated between about 50,000 and 10,000 years ago. And the timing tracks suspiciously closely with two overlapping events: rapid climate warming at the end of the last glacial period and the arrival of modern humans on continents that had never encountered our species before. World map, sequential human arrival dates overlaid with megafauna extinction dates by region. This is one of the genuinely open debates in paleontology, and any documentary claiming certainty here is overstating the science. In Australia, megafauna extinctions align closely with the earliest evidence of human arrival, well before major climate shifts, a pattern that points strongly toward human hunting, habitat burning, or both. In North America, the extinction wave follows both rapid climate change and human arrival within a similar window. And most researchers now favor some combination of the two pressures rather than either alone. What's not in serious dispute is the outcome. Earth lost the vast majority of its land animals, over roughly 45 kilograms in a geological eye blink. And the primary common factor across every continent is the arrival of one newly widespread, highly coordinated predator: us.
Before we go deeper, our goal on this video is to get 500 likes and share your reaction in the comments. Subscribe to the channel